After the screens, the sewage with all its suspended and soluble pollutants is directed to the subsequent unit. How do we remove the sand particles that may disturb the well-functioning of the bioreactors? In this lecture, we will discuss the principles and design of sand and grit removal units. Together with the sewage, a substantial fraction of sand is transported to the entrance of the sewage treatment plant. Sand has a higher density and settles much faster than the organic suspended solids. To prevent that the sand particles enter the bioreactor, which eventually leads to malfunctioning, sand and grit is removed in the so-called pre-treatment units. Generally, sand removal is directly positioned after the screening devices. Lowering of the liquid velocities in screens is restricted to 0.4 meters per second to prevent that sand settles in the screens. In the grit removal device, we lower the liquid velocity a bit further to make use of gravity separation to settle the sand. Gravity separation, or settling, or sedimentation, is one of the most common approaches to pre-treat or partially treat the domestic and municipal sewage flows. During gravity separation, we clarify the sewage flows from suspended matter, resulting in low turbidity liquid effluents and a concentrated stream of settled solids. Basically, we can distinguish two types of settling: discrete settling, flocculant settling. In discrete settling, the particle size, shape and specific density do not change in time. Discrete settling is regarded as a non-interactive settling of particles from a dilute suspension. For instance, the settling of grit and sand in water. During the settling, the particle velocity accelerates until a constant velocity is reached. Discrete settling can be mathematically described using the classical sedimentation laws of Newton and Stokes, as illustrated in this slide. In fact, there are two main forces enacting upon the particle, which are the gravity force and a drag force. The gravity force results from the particle characteristics and is directly dependent on the density difference between the particle and the liquid, multiplied by the gravitational acceleration and the volume of the particle. The drag force results from the motion of the particle through the liquid, and is thus dependent on the particle's velocity, as well as on the prevailing drag coefficient, the size of the particle and the liquid density. As the particle increases in velocity, eventually the drag force and the applied force will approximately equate, causing no further change in the particle's velocity. This velocity is known as the terminal velocity, settling velocity or fall velocity of the particle. This is readily measurable by examining the rate of fall of individual particles. The terminal velocity of the particle is affected by many parameters. In fact, anything that will alter the particle's drag. In addition to the particle density and the liquid viscosity and density, the terminal velocity is most notably dependent upon the particle's size and shape, symbolized by the so-called sphericity factor. For ideal spheres, this factor is 1, and for sand particles, the factor is 2. Factors exceeding 20 are used for fractal flocks. In non-stagnant medium, the drag force, CD, is dependent on the liquid flow regime or the level of liquid turbulence, as indicated by the upper three-term equation. The symbol NR stands for Reynolds number, which describes the liquid turbulence. Under laminar flow conditions, with Reynolds numbers less than 1, the drag coefficient is reciprocally correlated to Reynolds number, as illustrated in the slide. At low Reynolds number, only the first term of the equation determines the outcome. In the transition area, with Reynolds numbers between 1 and 2000, the drag coefficient should be calculated using the full three-term equation. At very high Reynolds number, larger than 2000, turbulence is not further impacting the drag force, which is then fixed as 0.34. The other type of settling is flocculant settling. During flocculant settling, particles agglomerate or coalesce or flocculate and have no constant characteristics. The particles vary in size and increase in mass, resulting in increased velocities during settling. Flocculant settling generally occurs with organic suspended solids, which are largely present in the domestic sewage and in our sewage treatment reactor. Flocculant settling can be divided in two subgroups: dilute suspension settling and hindered settling. In dilute suspension settling, particles are present in low concentrations, but generally higher than 50 milligrams per liter. Particles are free to coalesce with any other particle on the route of sedimentation, increasing their settling velocity. During the settling, the particles' motion do not cause significant water displacement. The settling efficiency is directly related to the hydraulic surface load and the hydraulic retention time. There are no mathematical formulas to describe the process, and sedimentation characteristics are determined by laboratory tests. The other type of flocculant settling is the so-called hindered settling. In principle, the same mechanism occurs as in dilute suspension settling. But at high suspended solids concentrations, the large quantities of particles cause multiple interactions, resulting in a slow downward movement of particles. The upward water movement further hinders settling. A clearly marked interface between sludge and supernatant liquid occurs. When time passes, the settled solids at the bottom further compress, leading to a density gradient from the bottom to the sludge-liquid interface, as illustrated in this graph. How can we apply the settling theory to the design of our grid chamber? Now, let's imagine we are going to design a rectangular grid chamber with a certain length, height and width. Next, we're going to apply a certain flow rate, Q. Now, let's imagine a certain particle with a certain settling velocity. Based on the applied Q, the width and the height of the grid chamber, the particle will flow with a certain horizontal velocity. Now, let's sediment the particle at a given flow rate. Great. The particle is removed from the liquid. Now let's take a new particle with a lower settleability and/or a higher horizontal flow. Oops, what you see? The tank is apparently too small. One more try, with another particle and a proper settleability and appropriate flow rate. A particle with discrete settling is retained in the grid chamber when the time required for vertical settling is less than the lasting time that the particles flow to the end of the tank. In other words, the ratio settling velocity to the height must be larger than the ratio horizontal velocity to the length. Since the horizontal velocity is determined by the Q and the vertical surface or height-width dimensions, the settling velocity must be larger than the surface velocity, which is the Q divided by the horizontal surface. The maximum allowable horizontal surface velocity or hydraulic surface load is also called the Hazen velocity. Now interestingly, this Hazen velocity is independent on the height of the grid chamber, as can be deduced from the above formulas. Having the Hazen velocity or maximum hydraulic surface load determined, we may understand that all particles with a settling velocity higher than the Hazen velocity will be removed from the waterline. Since the various particles are characterized by different settling velocities, often the feed inlet of the grid chamber is distributed over the height. What will be the impact of such feed inlet? Yes, indeed. Also particles with a lower settling velocity than the maximum hydraulic surface load will settle, and thus a higher removal efficiency. The most important design features of a rectangular grid chamber are therefore: the maximum hydraulic surface load or Hazen velocity should be below 40 cubic meter per square meter per hour, or 40 meter per hour, or 0.011 meter per second. 2. The critical horizontal velocity that may lift the sand from the bottom is 0.3 meter per second. This 0.3 meter per second is therefore called the critical scoring velocity or slip velocity. In our design, the resulting horizontal velocity must always be below this value. A design horizontal velocity close to the critical velocity will result in an excellent separation of sand particles from the organic fraction. Note that the critical scoring velocity of organic material is much lower. For instance, for primary sludge, the critical scoring velocity is 0.03 meter per second, which is 10 times less. The above design features will result in an efficient washing of the sand, which can be subsequently used for other purposes, like construction works. How much sand will be recovered at an average STP? Now, this will depend on the type of the sewerage applied, the extent of the sewer network, and size of the area served. For STPs treating the sewage of more than 100,000 inhabitants, the sand production is about 2 to 12 liters per person per year. So, a few containers per week. Owing to the high variations in sewage flow, generally various rectangular grid chambers are designed next to each other, which can be disconnected when not needed. The final design results in a number of, for instance, 4 long gutters, receiving a constant flow rate, having a constant discharge to the next process units. The maximum hydraulic surface load is 40 meters per hour, whereas the horizontal velocity or scoring velocity approximately is 0.3 meters per second. The generally applied length-width ratio ranges between 10 to 1 to 15 to 1. The clean sand is generally collected in a mechanized way as indicated in this slide. Instead of rectangular grid chambers, also square grid chambers are applied. In this design, the sand is moved to one lateral side by a slowly moving hopper. The collected sand is subsequently lifted and washed from organic solids using the incoming flow. Clean sand is subsequently collected, whereas the washed organic solids proceed away to the next process units. Some design features of a square grid chamber are: the water depth is 0.1 to 1 meter, tanks can be square or circular, maximum hydraulic surface load is 30 cubic meter per square meter per hour, or 30 meter per hour. The tank is characterized by a fluctuating discharge and is equipped with an external sand washer continuously washing the solids. Knowing the fundamentals of discrete settling, one can also use the liquid turbulence to increase the terminal velocity of the sand particles, enhancing separation. This is done in a so-called aerated grid chamber. Most organics will be separated from the sand particles, but a produced slurry will still contain a mixture that needs to be separated outside the tank. An interesting advantage of an aerated grid chamber is the accumulation of fat, oil and grease at the top of the chamber. This floating material can then be skimmed off, preventing possible problems in the bioreactors. The collected slurry from the grid chamber can be further cleaned by applying an hydrocyclone, which creates a concentrated downward stream with sand for discharge and a more light upward stream with organic suspended solids. The liquid overflow is returned to the main water stream. With the screens and the grid removal units, we removed most inorganic matter from the sewage. It's now time to have a look to the biological part of a system.